Good morning, everybody. Welcome to the plenary talk of this morning. Our speaker is from Japan, Professor Shimoyama. He is going to talk about recent progress in superconducting joint technologies connecting HTS materials. Professor Shimoyama, you may start anytime you want.
Thank you very much. How should I say? Good morning. Now, I'd like to start my talk. Before starting my talk, I'd like to say thank to the organizers of ICSM 2020, particularly to Professor Arigensa for inviting me. This is my second chance to attend this conference. The last one is 4 years ago. That was held at Fatih. There was a very nice place. Unfortunately, today I will attend this conference via website. Okay, anyway, I'd like to say one thing at the beginning. Fabrication of applicable superconducting joint connecting HTS tapes has been thought to be quite difficult until 5 years ago, even including me. But now I'm very happy to show our recent progresses in superconducting joint technologies connecting HTS materials. This is a very applicable method. And I thank to many researchers in the JST Mirai project who are listed here. And if you hear my talk till the end, you will find our technologies connecting Levico tapes and Visco tapes are not very difficult. You can trace our method without any difficulties. This is the content of my talk today. I will introduce what triggered us to development of superconducting joint between HTS, including I'm showing the 1.3 gigahertz NMR project conducted by JST program. And next, I will show the development of applicable joint connecting HTS tapes. So in this section, I'd like to discuss about the required conditions for superconducting joints we must take into account. And next, I will show the recent progresses in the superconducting joint connecting layers 1 to 3 tapes. And in this case, configuration and microstructure is very important point. I will show, including the desirable for oxygen annealing configuration and microstructures. So next, I show the similar topics on the Visco tapes. Configuration and microstructure is also very important for Visco tapes for grain coupling and between multi-filament tapes and the intermediate layers. And I will summarize my talk. So most of you know that superconducting joint technology have been already well established for low temperature superconductors. Develop superconducting magnets with persistent current circuits. So, for example, niobium-tin and niobium-3-tin, niobium-titanium, and those are the isotropic superconductivity with relatively long coherence lengths, approximately 5 nanometers. And superconducting coupling can be made with superconducting solids using such as bismuth, lead, and tin. So as you see here, you can see very nice superconducting joint between niobium titanium wires via solids. But in this case, also niobium titanium wires were twisted in the solid. In this case, direct contact between superconducting tapes improves in-field joint critical current performance. As you see here, even at 6 Tesla, very large current can flow through the joint. So this picture is very, very primitive one. You know that the superconducting ring can carry the persistent current. But in this case, superconducting magnet with a closed circuit and superconducting joint can save this very static magnetic field. That means energy storage between electric and magnetic, and very stable field is suitable for NMR and MRI systems. But anyway, the superconducting joint technology is indispensable to establish the persistent current circuit. So superconducting joint for the large superconducting magnet using very long length superconducting wires or tapes in total. That means length of commercial low temperature superconducting wires is usually longer than 1 kilometer. The point is that of HTS tapes is usually shorter than 500 meters. So if we consider such large superconducting magnet using HTS tapes, we need a large number of superconducting joints here around this magnet. This is very important point. Here, I'd like to discuss about the characteristic features of cuprate superconductors. Most of you know that all the cuprate superconductors has layered crystal structure with many constituent elements. Those shows high TC and very high HC2, but this means very short coherence length and superconductivity only occurred at coupled plane with the wave symmetry. Those result in the weak links at grain boundaries. Usually the JC in the crystal is much larger than the JC at the grain boundaries. And such alternate stacking of superconducting broken layers causes anisotropic physical properties. So this means that the JC critical current density along the AB plane is much higher than the critical current density along the axis. So at the same time, irreversibility field is much higher when we apply the magnetic field parallel to the AB plane. So many other characteristic features of cuprate superconductors are listed here, but the important point is the phase formation and grain coupling, grain growth occurs at very high temperature, above 800 degrees C. So these features suggested us those materials are unsuitable materials to fabricate superconducting joints. So, you know, in these days, we can buy many long cuprate superconducting tapes, Levco and Bisco. So now these lengths are longer than 1 kilometer. But the important point is when we remove the cap layer or metal sheath of those conductors, we can see clean, flat, and homogeneous crystal surface of cuprate superconductors. That means crystallinity of superconducting crystal is very high at the top of the superconducting layer of those tapes. That means less reactive layer. So now I'd like to show the development of applicable superconducting joints connecting HTS tapes. As a beginning, I'd like to introduce the JSMIRAI program. Those are the large-scale type projects continuing 10 years, and each seems has a big budget, about $40 million for 10 years. So our project is this: high temperature superconducting wire joint technologies leading to innovation. This program started about 4 years ago and will continue 2026. So in this program, we develop superconducting joint technologies applicable for superconducting feeder cable for railway systems, as well as 1.3 gigahertz superconducting magnet for animal applications with persistent mode. So this is the organization of our program. The program manager is Professor Hideaki Maeda, and this is me, and many other famous professors and researchers are included in this program. The important point is this program is consisted of 15 research institutes, university, and companies. So this is the basic design of 1.3 gigahertz. That means 30.5 Tesla animal magnet. This is a very big one, as you see here. And you can see 4 superconductors are used in this magnet: niobium, titanium, niobium 13, and visco 223, and Levco coated conductors. The operating current is now designed to be 231 amps, and operating temperature is 4.2 Kelvin. Self-inductance of this big magnet is very large, 988 Henry, and stored energy is very large, 26.4 megajoule. So the HTS in the coils are layer winding and Levco and visco 223. And current density for those HTS materials are 205 amps for Levco and 137 amps for visco 2223. This is the current density for per square millimeters. Then, if you see this graph, you can find the field contribution of HTS is very large. In total, 15.9 Tesla will be generated by the HTS, Levco and visco 2223. And Levco generates 8.7 Tesla, and visco 223 generates 7 Tesla, while the low TC superconducting coils generates 15.1 Tesla. So conductor length is very long. Levco 5.2 kilometers, visco 11 kilometers, and LTS 154 kilometers. So this is the important point. The number of joints is very large. Levco joint is designed to be 17 joints, and the number of visco joints is ranging from 30 to 45. Very, very large number of joints will be needed to construct this big magnet. So if you see this circuit, these coils are connected seriously, one loop you see here, and there are many joints. So inside the bismuth 223 magnets, many joints here. Inside the Levco coils, you see here many joints here. The number is listed here again. So due to the very large self-inductance of big magnet, so if we want to achieve very low field drift rate, less than 0.01 ppm per hour, allows us to relatively large circuit resistance. This is calculated to be 2.75 times 10 to minus 9 ohms. Therefore, we must design total resistance of this circuit smaller than this value. In the current design, the calculated or designed, total resistance of the big coil is less than 1.2 times 10 to minus 9 ohms. This satisfies this requirement. So anyway, all of superconducting joints connecting Lebuco and Bisco and Bisco satisfies very low resistance, less than 10 to minus 12 ohms. This is very challenging values. So after construction of the big coil, we will find such modern art, including many HTS joints. But the important point is all of the joints will be placed at low field part from the big magnet. The center position, the magnetic field is over 30 Tesla, while the magnetic field at the HTS joint less than 1 Tesla. So this figure shows a collaboration group of basic technology for development of joints in the JS Mirai project. BB joint means bismuth joint. So our group is now studying on the indirect superconducting joint between the BISCO 223 tapes using bismuth 223 intermediate layer. And another approach is made by Professor Kanazawa at Murata Institute Technology. He's trying to develop a new process, direct superconducting joint between BISCO 223 tapes by merit solidification. In this case, BISCO tapes were connected by bismuth 2212 phase. For RR joint, indirect superconducting joint between gadolinium 1-3 tapes be epitaxially grown intermediate gadolinium 1-3 layer. This study is conducted by the Sumitomo Electric Industries. And we need another joint, Lebuco and LTS or Bisco and LTS. In this case, we are trying to develop very low resistance joint below 0.1 nano connecting layers 1 to 3 tape or Bisco 2 to 3 tape with 9-beam wire using Solider. This study is now conducted by the National Institute for Material Science, NIMS. So anyway, this is the target performance of the superconducting joint between the HTS tapes at Mirai project. As I told you, BB joint and RR joint needs very low joint resistance at 4.2 Kelvin in a field lower than 1 Tesla, that is 10 to minus 12 ohms, and applying current 231 amps. So let me think about the direct superconducting joint and indirect superconducting joint. As I said before, HTS tapes, well-fabricated HTS tapes have very well crystallized surface. This is high crystallinity. That is less reactive. Therefore, it is very hard to connect only by sintering. In the case of the direct superconducting joint, you see superconducting layer connected directly in this way. Merit solidification process is necessary for direct superconducting joint, such as layers 1 to 3 and bismuth 2 to 1 2. So, however, merit solidified layers 1 to 3 needs oxygen annealing for a very, very long time because of very long diffusion path for oxygen. And merit solidification technique cannot be applied for bismuth 2223. On the other hand, indirect superconducting joint by sandwiching the intermediate layer, as you see here. So, on indirect superconducting joint, be a reactive intermediate layer is more versatile, I believe. Superconducting joint can be formed by heating without generation of melt. This technique can be applied for layers 1 to 3 and BISCO 2 to 3. So achieving in a large IC at interface and intermediate layer is essential because high JC is already achieved in the superconducting layer of the tapes. However, intermediate layer have very sometimes just like a sintered bulk structure. In this case, we must increase the JC of intermediate layer connecting these two tapes. However, high JC is not always needed here because the contact area is very large. So therefore, less than 10 amps per square millimeter of JC is enough for intermediate layers. So here I listed the required condition of superconducting joint connecting HTS tapes. At first, without significant degradation of superconducting properties, HTS tapes after heat treatment for superconducting joint above 800 degrees C. And second, and moderate carrier doping state achieved as a joint region by positioning. This is a very important point for layers 1 to 3 systems, as I discuss later. Mechanically and electrically well-connected homogeneous interface in terms of both between HTS tapes or HTS tapes and the intermediate layer is very important. And force is also important, robust against heat cycles. So, and electromagnetic force. So, these 2 points are very essential to construct a real superconducting magnet. Without using special techniques such as vacuum or high gas pressure processes. The second one is a simple method with high reproducibility can be performed near coils in a short time, hopefully within 2 days. From now, I'd like to show the recent progresses in the superconducting joint connecting layers 1 to 3 tapes. Most of you know that the layers 1 to 3 system have very large oxygen non-stoichiometry from oxygen content 6 to 7. So this is the synthesis condition. However, to obtain 90 Kelvin class superconducting properties, we must increase the oxygen content by oxygen annealing. So on most of the case, we use gadolinium in this case. To achieve the maximum TC for gadolinium 1 to 3, we must anneal the gadolinium 1 to 3 joint at around 300 or 350 degrees C in flowing oxygen. However, such low temperature, diffusion coefficient of oxygen is very small. That means oxygen annealing should need very long time. So in fact, in the case of the bulk samples, so this is the case of the dysprosium 1 to 3 bulks, it takes very long time for oxygen loading into these bulk samples. So at about 100 hours in flowing oxygen. So this is the first successful superconducting joint between HTS tapes with large joint IC. This report was published in 7 years ago. They prepared gadolinium joint by melt solidification. Gadolinium 1 to 3 tapes are connected in this way by melt solidification. However, they must make 464 microholes in joining area to introduce oxygen after melt solidification. In their method, they applied oxygen annealing at 500 degrees C, 350 hours in relatively high oxygen pressure, 0.7 megapascals. So why oxygen diffusion is very slow in this case? Large crystals with few defects formed after melt solidification. This means that without a fast oxygen diffusion path. So in the case of the superconducting bulks, in this case, yttrium 1 to 3 melt solidified bulks can be grown on the gadolinium 1 to 3 melt solidified seed plate in this way. We can grow such big crystals in a short time. On the other hand, epitaxial growth of layers 1 to 3 on already prepared layers 1 to 3 biaxial oriented film by fluorine-free MOD, metal organic decomposition method. So in this case, total thickness of the film is 3 micron, but this sample was sintered for 6 times. Sintering, painting, sintering and painting, we repeated 6 times to obtain such thick films. But the crystal orientation is same all over the films. This is a hint. When we think about the oxygen non-stoichiometry of 1 to 3 systems, this is conditions for film synthesis, but this is high superconducting temperature regions. When we consider oxygen diffusion rate in the orthorhombic regions, relatively slow oxygen diffusion in perfect crystals. However, thin boundaries can act as fast diffusion paths as well as small angle grain boundaries on the 2D conductors also act as a fast diffusion path. In the tetragonal phase, oxygen diffusion is relatively fast, but not very fast. Also in this case, small angle grain boundaries can act as a fast diffusion path. So considering the oxygen diffusion path, we should not melt of the 2D layers to reserve the small angle grain boundaries. If we put joint piece on the 2 tapes in this way, with intermediate layer, as is here, there are small angle grain boundaries. In this case, oxygen can diffuse from 4 directions through the small angle grain boundaries. So this idea was realized in the IGS joint developed by Sumitomo Electric companies. IGS means intermediate grown superconducting. The base value of the joint IC is 161 amps at 77 Kelvin, while the coated conductor IC is only 200 amps. In this method, they use intermediate layers is here. I will introduce this technique precisely. So this IGS joint can carry large current at 4 Kelvin. As you see here, even in 1 Tesla, more than 700 amps of critical current can flow through the joint intermediate layer. And when we make closed circuit and measure the decay of the magnetic field in the coil, after 3 days, we found that very slow decay and calculated resistance is around 5.4 times 10 to minus 13 amps. Oh, sorry. The key technology of this joint is preparation of intermediate layers is here. polycrystalline precursor layer on the 2D conductors. And joining strap and coated coated conductors are pressed together with intermediate layer, as you see here, about 40 megapascals. And heat treatment at 800 degrees C in low pH atmosphere, around 10 to minus 4 atm at 800 degrees C here is the crystal growth conditions. The leaf layer grown epitaxially. And important point is the small angle grain boundaries are included also in the new intermediate layer. So in this case, oxidation annealing in flowing oxygen at 500 degrees C to 200 degrees C for 6 hours are enough to introduce oxygen to be 90 Kelvin class superconductors due to the presence of the small angle grain boundaries. So here I'd like to introduce you briefly about this method again. At the beginning, precursor layer composed of microcrystals of yttrium-123 on the gadolinium 123 short conductors. This is a joint piece, joint strap. So sintering at 800 degrees C and 40 minutes in pure oxygen is important to prepare such precursor layers. Such thick precursor layer shrinks by heating 800 degrees C for 1 minute in reducing atmosphere under applying pressure in this way. And then such sintering time increased to 20 minutes. The structure is almost the same, but let we see more precisely about this scheme. So this is a precursor layer, thick layer, turns to very dense and thin intermediate layer after heating 800 degrees C for 1 minute or 20 minutes. If we look at carefully at the interface between strap and precursor layer, this picture is taken for the sample heated at 800 degrees C for 40 minutes in pure oxygen. There are many small grains, yttrium-123 grains here. But if you see here, very small regions composed of axis-oriented layers and a-axis-oriented layer were found at the interface. After sintering at 800 degrees C for 1 minute in reducing atmosphere, the axis-oriented intermediate layer started to grow from the interface, as you see here. The middle part of the intermediate layer remained randomly oriented small grains. After 20 minutes, all the intermediate layer turns to very well crystallized gadolinium yttrium-123 layers, as you see here. So the important point is directions of directions a-axis of two regions, upper part of the grain boundary and lower part of the grain boundaries must be the same. This means that the direction of a-axis in DDBCO, coated conductor, and strap must be the same. This is only one important point we must take into account. So to evaluate joint performance more precisely, NIMS developed the joint resistance evaluation system. This is a very sensitive system, as you see here. This is the injection coil, and this is the coil, and the joint exists here. So in this case, Hall sensor is located here to detect the current decay. So if we put the joint part into the superconducting magnet, we can measure joint performance in the magnetic field up to 3 Tesla. With these systems, we can evaluate the joint resistance down to 10 to minus 15 ohms. This is very, very sensitive method. So for the gadolinium conductors joined by the intermediate layer, current decay is very, very small at 4.2 Kelvin, as you see here. Even under the injecting current over 300 amps, current decay with time is very, very small. And in this case, we can calculate the joint resistance to be almost 10 to minus 14 ohms. This is much lower than the required values. So at 77 Kelvin, so in this case, the joint IC is 160 amps. However, this joint can carry large current up to 100 amps without serious decay. In this case, joint resistance were 2 times 10 to minus 13 ohms. This also requires values 10 to minus 12 ohms. So in field performance at 77 Kelvin is not so nice. Only at 0 Tesla, we can observe very slow current decay, while at 4.2 Kelvin, even at 3 Tesla, this joint can carry large current without showing large decrease in current. As you see here, the calculated joint resistance is in the order of 10 to minus 14 ohms, very low. This completely a superconducting joint. This is a summarized result for the superconducting joint resistance, as you see here. At 4.2 Kelvin, up to 3 Tesla, we can flow large current with a decay of a current through the superconducting joint. At 77 Kelvin, only at low field, we can expect persistent current circuit. So such very nice performance was also confirmed in the persistent NMR magnet using IDES joint. So this is the IDES joint. There are 2 joints exist here in this closed circuit, and this closed circuit was installed in the 400 megahertz NMR systems and operated for longer than 700 days, as you see here. Very small change in the magnetic field in the NMR magnet was confirmed. This means the joint resistance is much lower in the 10 to minus 15 ohms for a long time.
10 minutes left, Professor
Okay,
Shimoyama.
yeah, it's good. It's good. Very nice. Thank you very much. Now I move to the topics on the BISCO 223 tapes. So in the case of the BISCO 2212, multifilamentary round wire were developed by the partial melting method. Also for the superconducting joint, partial melting method can be applied for the BISCO 2212 systems. As you see here, partial melting point is here, and slow cooling conducts very good grain growth as an interface that connects the bismuth 2212 filaments, makes the very strong connections by melt solidification, and resulting in very high joint IC at 4.2 Kelvin, even at 14 Tesla. However, this technique cannot be applied for our program because we use BISCO 2223 tapes. So about the BISCO 2223 tapes, in these 15 years, we mainly use the DI BISCO tape developed by Sumitomo Electric companies. By using these tapes, we can expect very large critical current up to high temperatures. For example, at 77 Kelvin, critical current is around 200 amps, and length is very long. And using such big furnaces, we can obtain very long length tapes in total over 50 kilometers for one batch. But this tape is composed of multi-filament with 121 filaments inside the silver sheath. So this is the specification of the DI visco tapes. The bare superconducting tape, we say type H. Bare means a silver sheath tape without reinforcement, has very low critical tensile stress, 130 megapascal. This cannot be used for the superconducting magnet in generating very high field, because electromagnetic force is much larger than this value. So we will use this type HDNX tapes in our program. These tapes are reinforced by the nickel alloy, and the critical tensile stress is around 400 megapascal. This is high enough to be used in our program. But the problem is type HDNX tapes is not so long, approximately 500 meters is the longest, because we must set the nickel alloy both sides of the tapes. So thus far, why superconducting joint has not been established for visco 223 tapes? I listed previous reports here. Very low values of joint IC at 77 Kelvin. But those studies are done by using monocore tapes, not multifilamentary tapes. But we found very large joint IC for the bulk materials, as you see here. In this case, joint IC exceeds is close to 200 amps, but the joint JC is not so high, 100 amps per square centimeter or something like. Anyway, we must develop good joint method connecting visco 223 multifilamentary tapes. So to prepare superconducting joint with high IC for visco 223 tapes, at the beginning, we developed a very high IC visco 223 thick films, as you see here. By pressing, we can prepare slightly axis-oriented thick films of visco 223 layer, and this thick film can carry large current, as you see here, JC of 50 kiloamps per square centimeter at 4.2 Kelvin. But in the case of the visco systems, we don't need worry about oxygen content. This is much different case from the layers 1 to 3, because the TC is not so much sensitive against the oxygen annealing temperatures. So at the beginning, we prepare the superconducting joint, as you see here, only on the top surface of the multifilamentary wires. This is intermediate layers. But in this case, only 10 or 15 filaments or 121 filaments are connected by this layer. The critical current is very low, only 10 amps. But very old patents suggested us very good hint. If we prepare such surfaces showing very large number of filaments, so if we connect these two tapes, we can expect very high joint IC between visco 223 tapes. The important technology is shown here. By pressing the visco 223 tape with very shallow angle, 0.4 to 0.6 from the tape surface, we can see many filaments after pressing. So these two tapes are connected by visco 223 thick films, and yeah, very good connection between the polycrystalline layer and the visco filaments. So if by increasing the number of the filaments, joint IC increase in this way. Those three joints carries very large current over 80 amps, and number of joined filaments are around 100 of 121 filaments. Very large values were realized even for the visco 2223 superconducting joints. So this joint is very robust against the temperature hysteresis and field hysteresis as is here. At 4 Kelvin, this joint can carry about 400 amps without showing any degradation.
Professor
However,
Shimoyama,
oh,
Professor Shimoyama, we have a couple of minutes only.
yeah, 3 minutes, I believe. Okay. We developed the termination joint as you see here. This is a schematic drawing of this joint part. This is almost parallel joint as you see here. This means the current flows AB direction, even in the joint layer. Also for this joint configurations, we can develop 100 amps class joint between visco 223 tapes, and this joint can carry very high current at 4 Kelvin with showing big hysteresis. This means the weak nature of polycrystalline layer still remains at the intermediate layers. So current decay measurements were also performed for this joint, and we confirmed at 4 Kelvin, current decay rate is very small, while at 77 Kelvin, at 100 Kelvin, current decay ratio is relatively large. However, we can observe the persistent current even at 100 Kelvin for this joint, because the joint TC is 105 Kelvin. So in field performance is also nice, up to 2 Tesla. This kind of visco joint kept very low joint resistance below 10 to minus 13 ohms. This is well required. This value is well satisfied our target performance in our project. However, at 20 Kelvin, such best nice performance is only observed at 0 Tesla or 1 Tesla. So this is the last slide. So in this program, we will use reinforced tapes. But in the case of reinforced tapes, we must remove the reinforced nickel alloys connected by the soliders. So we need additional procedure as you see here. To remove the nickel alloy tape by heating above melting point of solider and removal of tin and silver tin alloy by electrolysis and in this way. However, through these additional procedures, we obtain type H tapes. Therefore, high critical current properties were also observed in the reinforced tapes, even in the superconducting joint. So I'd like to summarize my talk. Development of superconducting joint connecting HS tapes is in rapid progress and a Mirai project. Joint technologies using intermediate superconducting layer adapted in a project are very promising and to achieve enough high joint RC properties with high reproducibility. We are almost ready to transfer superconducting joint technologies, both Rebico joint and Visco joint, to the company, Justic, who constructs 1.3 gigahertz NMR magnet. And both RR joints and VV joints can be widely used for magnet systems operating at middle temperatures, 20 to 77 Kelvin, if the joints are placed in low magnetic field, and used under small tensile stress. So this is the message by Albert Einstein. Everything should be made as possible, simple as possible, but not simpler. This is my last message. HDS joints should be made as simple as possible, but not simple. Thank you very much.
We thank Professor Shimoyama for his comprehensive presentation. Now, do we have any questions from the hall? I do have a question, Professor. Have you considered use of MJB2 wires in 1.3 gigahertz NMR magnet?
Oh, MDB2 has relatively low irreversibility field, even at 4.2 Kelvin. Therefore, we didn't select MDB2 conductors to construct 30.5 Tesla magnet.
Okay. I have another question actually. When you make the joints, did you or have you experienced any damage to the tapes?
Oh, it's a good question. So, as I told you, when we prepare the superconducting joints, both RR and BB, we need heat treatment at around 800 degrees C. By such heat treatment, superconducting properties of the tape slightly degraded. For example, Visco 223 tapes, which has an IC of around 200 amps before preparation of the joint. However, after preparation of joints, 200 amps, after preparation of joints, this value decreases down to 150 amps. In the case of the Levco, it is more complicated. Essentially, such degradation should not occur in the Levco system. However, introduction of oxygen is very important. So if oxidation is not sufficiently performed, superconducting properties of the Levco tapes may degrade. It depends on the oxygen annealing conditions.
Okay, thank you very much. Ali Gencer has a question.
I don't know how to ask the question, Professor Shimoyama. With the low resistance in the joints that you have succeeded, is it possible to have a persistent mode magnet made using Repco tapes at the moment?
Yes.
Okay. How do
but,
you?
But we must place a joint at the outside of coil.
Outside of the coil?
Yeah, because the electromagnetic force is very large when we put the joint at the coil. So the mechanical properties against the tensile stress is not good for both joints.
Okay. Now the issue is that you can eliminate the effect of magnetic field on the joints with this arrangement.
Yes. Yes, like this.
Yeah. Okay. Right. Okay, I understand.
And we can use the magnetic shielding technique. So we can reduce the magnetic field down to 0.2 Tesla or something like. In this case, we can use these joints at higher temperatures, 20 Kelvin, 40 Kelvin, and even at 77 Kelvin, I believe.
So did you try at 77 Kelvin liquid nitrogen temperature?
Yeah, I want to try, but it's not scheduled in our program.
Okay, thank you.
Is there any question from the Zoom? Can you show it on the screen? Or Professor Shimoyama, can you see the questions from the Zoom on your screen?
Oh, screen,
Chat area?
chat area?
No.
Okay.
Okay. No questions from the Zoom. Any more questions
No.
from? Okay.
Mhm.
Any questions from the
No.
hall?
Yeah,
No.
I found one question from, please.
Okay.
Hello. Thank you,
you.
Professor Shimoyama. It's very exciting. It's a very exciting talk. So do you consider how much field inside of NMR magnet will be distorted if you remove that, connections outside of that?
Oh, do you mean inside the magnet? Sorry, I can catch the meaning of questions.
I think it's
Sorry. Please repeat again.
so if we remove the contact point from that coil, we
Contact?
presumably distorted magnetic field inside of the coil. And for NMR magnets, it's very important field uniformity.
Yeah.
So do you estimate what will be the distortion level? Thank you.
I'm not professional about the magnet design for NMR systems. However, Dr. Yanagisawa is very professional for designing such magnet, including the calculation of distortion.
Okay.
I think this is very challenging because nobody experienced at 30.5 Tesla magnet. I don't know what will happen when we start to operate NMR systems.
Thank you so much. Yes, it's very challenging, but you get persistent joints, which is the important part of that. Yes. Thank you.
Yeah, thank you very much.
Have a nice day and good meeting after this, Professor Shimoyama.
Thank
We
you.
stay in touch for future collaborations between Turkey and Japan.
Okay, see you in Tokyo again. Bye-bye.